Our next speaker is Professor Cornelius Nielsch from the Leibniz Institute for Solid State and Materials Research. He's the professor and director of metallic material over there. And he will have a talk on the application of thermoelectrics for energy production and cooling. And then we continue the session with Luis Albardero. And then we will have lunch at 12:50 for 1 hour. So Cornelius.
Okay, thank you for the kind introduction. And also Philip, thanks for the invitation to this, I think, very productive workshop. So I will, I think, give, let's say, a short introduction of myself. And let's see, I see the change of the slides, but it's not. Okay, yeah. So I'm from IFW Dresden, which is Leibniz Institute. It's about roughly, I think, about 100 Leibniz Institute. The mission we have is going from fundamentals to application. So we are somehow in between Max Planck and also the Fraunhofer Institutes, and we are located, let's say, in the beautiful, I think, landscape of the Dresden Elbe Valley. And I think we have rather, I think, good conditions to perform our research there. So at the IFW in Dresden, we have about roughly 500 employees, about 300 scientists. In my unit, which I'm directly, I think, supervising, it's about 100 people, 100, let's say, 30 PhD students. It's a whole institute, and then also we have a very good support by technicians, for example, which are working on the, for example, development of thermoelectric modules. So what I think Antonio already mentioned in the previous talk is that the main, let's say, application field for thermoelectrics, if you look from a commercial standpoint of view, it's thermoelectric cooling. So this is, I think, the biggest market up to now. 70–80% is for thermoelectric cooling. There is also, I think, this is a great vision so far also to use waste heat for the thermoelectric applications and power in principle to produce electricity. I mean, the challenging part here I see from my point of view is that we have, I think, with each different, let's say, application, we have very different application scenarios. So we need actually quite different modules for each application scenario. And this makes the use of waste heat or the waste heat recovery quite challenging, I would say. In photovoltaics, I mean, you have the spectra of the sun, which is, I think, quite standardized. You just, I think, focus your application to fit ideally, I think, to the spectra. Whereas if we have, for example, here different scenarios, like, for example, steel industry, where you have maybe very high, let's say, high heats in the range of 1,000 degrees, for example, for very short time. Or in the car, for example, where you have maybe a temperature gradient of 400–500 centigrade. These are already quite different scenarios. I will show at the beginning some we have done with a company in Aachen together, some survey where are, let's say, in principle, the markets for thermoelectric devices. And I bring up a brief, let's say, summary. Where are the actual market, where are potential future market for thermoelectric applications? So one of the current biggest market, I think, is telecommunication, especially stabilizing here solid-state lasers and using thermoelectrics for the temperature control in a, let's say, rather narrow window to stabilize the frequencies of these lasers and also the whole devices. And in principle, it's a very big market at the moment already. I mean, this is probably the whole telecommunication market, but thermoelectrics gives a huge contribution to this market. And there's also the demand to especially develop very small thermoelectric devices, so with a footprint of millimeters, for example. Sometimes there are also ideas to integrate it in chips, but this is, I think, a more advanced technology. Another field, I think, which is also, I think, where thermoelectrics can, I think, strongly contribute are I think, control of, let's say, medical instruments. And there are different, let's say, areas where you can apply it. I mean, you can, on one hand, you have also here also the temperature control on a very precise level. This is one thing you want to do it. I think where you have, for example, a small footprint and you would just want to cool this small area. This is, I think, here, I think, thermoelectrics is quite useful. There are a number, I think, here of different applications. So this is quite a diversity of things. You can, in liquid chromatographies, in, for example, centrifuges, for example, you want to cool it down. CO2 incubators, for example, climate chambers, and also thermal cycling. Here, I think thermoelectrics is quite important. When you want to reach a certain temperature relatively fast on the time frame of seconds, for example, then I think thermoelectrics is the most ideal thing you can use. Also, I think in principle it's a solid state device, no moving parts. And this makes it, I think, very, I think reliable to use in this I think area. There's probably a worth to organize a separate workshop just for this area, because the devices in these areas are quite diverse, and but it's a huge market, I think, for thermoelectric modules. And I also know from Quickhome, for example, a company who's selling, I think, the highest number of thermoelectric modules in Germany. They are, I think, collaborating with a number, I think, of these companies fabricating such devices. Another, I think, market for thermoelectric devices is in principle the semiconductor industry. And there you also have the demand that you want to, for example, test chips on a rather small scale. You want to, in principle, stabilize the temperature in the range between, let's say, 0 degrees and 100 degrees. Also do rapid thermal cycling, for example, to test how robust are these chips, for example. And these are also specialized, I think, instruments where thermoelectric coolers are used, I think, on larger scales. Another market is also more industrial, I think, industrial driven, is, I think, all the area of industrial lasers, for example. And here you want to also stabilize the temperature, control it quite precisely. You also have, for the control of some of the components in these devices, you want to use thermoelectrics to, for example, to stabilize the temperature. But on the other hand, also to get rid of, I think, especially here, is excessive heat produced in these devices. So this is one of the markets where thermoelectric devices are used. And I think the thermoelectric is probably useful up to, let's say, in the 1 kilowatt, I think, range. But this is a really high, I think, heat, I think, amount which has to be removed. Following, in principle, the same trend, cooling for additive manufacturing. I think this is, I think, also a booming field at the moment. You can, in principle, use also lasers here to in principle, manufacture in three-dimensional ways, I think, materials. But there are also, I think, other techniques like extrusion printing, dispenser printing, for example, where thermoelectrics can be used and where precise temperature control makes quite sense. Here also, I think you can use, especially that you can produce, I think, a temperature gradient in the range of 70, for example, centigrade. I think on a small spot rather rapidly with thermoelectric cooling, and this, I think, helps quite well, I think, to stabilize and control much better the three-dimensional printing process by thermoelectrics. Then this is, I think, a market which is probably not existing, but there are currently some discussions about it. So since we are dealing more and more with liquefied natural gas, and to actually use a liquefied natural gas, you want to, in principle, vaporize the gas, and from the way that you go from the, let's say, cryogenically cooled, I think, liquid to the gas, which you might later on burn, you have here already a temperature gradient of 170, 180 centigrade. So quite a huge, I think, temperature gradient you could use. And based on this, I think, from this evaporation process, you can, for example, per ton of liquid gas, you can produce about 840 megajoules per ton. So this might be, I think, quite attractive to use thermoelectrics here, especially in these gas terminals in the harbors, to produce a lot of, let's say, electricity from this evaporation process. This is definitely one, let's say, area where thermoelectrics could definitely be used to do, in principle, the not waste heat recovery, but waste cold recovery, to use here thermoelectrics. And there are actually also at the moment a project going on between, I think, Daimler Truck Company and also DLR in Stuttgart, where they also want to use, in principle, in trucks, in principle, thermoelectrics at very low temperatures to recover the waste cold. This is, I think, more, this is what comes here now. It's more, I would say, more an academic, let's say, maybe scenario. I don't think there's a big market, but at least it was, I think, published, I think, in a prominent journal recently. It was the idea, okay, that you can maybe also use thermoelectrics in combination with solar cells, even to produce electricity during the night. So the idea is you have maybe here, I think, a heat reservoir, maybe the ground, for example. This provides, I think, a lot of, let's say, heat during the night. The whole solar cell is cooling down, emitting here the heat to the air, and then you can, in principle, in a reverse process, use here the heat coming from the ground to harvest with the thermoelectric module. And here you would use a very small temperature gradient. So most likely, I mean, if I look on this very small temperature gradient, it's probably not very productive to produce large amount of electricity, but it's at least a scenario. Okay, coming back, I think, to transport of, let's say, fossil fuels. There's a lot of demand for pipeline monitoring. For safety of these pipelines, but also I think one reason is also in some areas of the world you don't know how much, let's say, you directly should receive, and when you send it there, so there might be some, let's say, leakages during the transport, and you also want to monitor it. And for this pipeline monitoring, I think you can use thermoelectrics for energy autark sensors. So you have locally an autark, let's say, system, which is in principle using the temperature gradient provided here, for example, by the temperature of the oil versus the ambient condition, for example. This works the same with oil pipelines, but also with gas pipelines. And this is can be quite helpful, I think, for the monitoring of these pipelines. And then this is another scenario, which is, I think, at least under discussion. There's a company, Green Fluidics in Mexico. They're using some kind, it looks like more a solar cell, but their idea is to, in principle, grow and harvest algae and use these, I think, devices for CO2 capture. And this is also producing a lot of, I think, heat, waste heat, which can be maybe, I think, also utilized by thermoelectrics. These are some scenarios discussed, might not be a big market, but at least these are some scenarios which could be used. Okay, this was a bit an overview, what could be potentially be done in thermoelectrics, I think, in the future, and also what is done partly, I think, up to now. Now we'll talk more about what we have done, and also introduce shortly, I think, another device which works a bit different, or not different, looks a bit different than the standard thermoelectric device. So we have worked for a while within European project on microstructured thermoelectric devices. The material we have used, in terms of thermoelectric performance, are rather decent, but we managed to have a very low contact resistance in these devices. And you can use these devices, for example, to stabilize the temperature of solid-state lasers and integrate it directly with a solid-state laser, these devices. The advantage of these devices are that you can stabilize temperatures within milliseconds. So the standard thermoelectric device would stabilize the temperature in seconds. This could stabilize the temperature within milliseconds. So you have a much smaller thermal mass, and therefore you can, I think, much rapidly, I think, react. And on the other hand, since you have so many legs here on a rather small footprint, you can also produce a rather high voltage with these devices. And this could also open, I think, up a number of new applications. So this is, I think, for give you an overview, what could be done if you, I think, miniaturize these thermoelectric devices. So you can think about, let's say, hotspot cooling, definitely. You can also think about here powering IoT devices. There we have also one project at the moment running. Also, I think here, if you bring it together with, for example, microfluidics. You can maybe use it for biotechnology or medical applications, for example. And yeah, the stabilization of lasers, I think, on a small footprint is also one of the ideas which could be done. And in this area, if we just focus now on microstructured thermoelectric devices, which is, I think, within the thermoelectric community, quite niche, let's say, research field, they have in principle three different, let's say, three different strategies to produce it. One of the strategies, you just scale down the standard thermoelectric module, and this we can call it mini bulk or baby bulk or whatever. And this, I think, you can buy, I think, rather tiny thermoelectric modules already on a footprint of, let's say, few square millimeters, for example. This works quite reliable, and they have also the highest efficiency, and these have been also introduced, for example, to operate these watches, for example. Then there's also the idea to use silicon technology. So they integrate the whole fabrication process into, let's say, the microstructure silicon technology. You can also, I think, bring it, let's say, on the chip. There are also some ideas, discussions about new silicon-based material for thermoelectric applications. And there are also some number of harvesting devices have been reported. Then there's a third branch where we have been active for a while, which is in the MEM space, where we combine, for example, microstructure technology and also electrochemistry, and then grow these microstructure devices quite, I think, in a quite reliable and successful way. And then there's a fourth branch, where I think people using more additive manufacturing techniques and also chemical synthesis approaches and do 3D printing, for example, of thermoelectric devices. They're especially in US and also Korea, quite active group in these areas to fabricate partly flexible devices, but also, I think, introducing a number of new materials by using this 3D printing technique. Okay, now I come to the second part of my presentation, where I want to shortly talk about how we come from a material to a thermoelectric device and using especially the magnesium antimonide. I mean, this has been, you have already addressed a number of points, and there are also some of the tricky points I also will address here. That in principle, magnesium is at the moment the most promising material to replace the bismuth telluride-based materials. If you look, for example, here on these are the two, I think, important components, the P-type bismuth antimon-telluride and the N-type bismuth telluride selenide. These are, I think, the material which are 95% of all thermoelectric devices which are commercially available. And if you look on a lot of development in recent years, they're mostly here at higher temperatures. So they're not really useful to use them for thermoelectric cooling, for example. And they are also so far, I think, most of these, I think, or not most of them, a lot of these materials have not been really tested in devices. So our strategy is to use these two compounds, magnesium bismuth antimonide. You see very high performance here around room temperature. This is the N-type material, very promising. And I think the prediction was, I mean, for a very long time, it was known that it could be a very promising material, but the people have not figured out how you can solve the issue that you lose to magnesium during the fabrication process. So nowadays, you usually work with an excess of about 10–20% of magnesium to stabilize the compound during the hot pressing, and this helps to stabilize and reach these high ZT values. The performance of the P-type material is rather moderate. We have done some improvements, but you can see here the P-type material is a low performer, I would say, but it's okay. Therefore, we decided to take the P-type magnesium silver antimonide. There are some issues about phase transitions. I also will shortly address it. But this combination could be used, for example, for thermoelectric cooling, but also for low temperature waste heat recovery. Here, one comment about the phase transition in magnesium silver antimonide. So up to 300 centigrade, this works quite nicely. You have this gamma phase magnesium silver antimonide, and this, I think, is very robust, I would say. If you go beyond 300 centigrade, then you have the transformation to beta. This is still okay, but you don't want to reach the gamma phase, the alpha phase of magnesium silver antimonide, because it's also not really reversible, and therefore you try to stay away. So you should not treat your device beyond 300 centigrade. And also, I think what was also challenged at the beginning was that the fabrication process was rather lengthy. You can see here fabricating the material, hot pressing, and then annealing for 7 days. So in terms of industrial production, this is not very attractive. You will probably, I think, have to pay a quite high electricity bill. So therefore, we have decided, okay, let's do it in a, I think, much faster way. So we directly do bulk mechanical alloying, take directly the elements. Also, in order to simplify the contacting, we directly compact these materials together with the thermoelectric material when we compact it. And we use, for example, for the magnesium silver, antimonide silver as a contact material. And for the N-type material, we use iron as a contact material. Here, just an impression how, for example, these contacts look like. Here we have, for example, the transition between silver and magnesium silver antimonide. I think there's a quite nice, interface. There's also no, let's say, the large intermixing zone. And the same holds also when we have now the N-type material with the iron, for example. We have also a good transition between both materials. One strategy to boost especially the efficiency of these modules from the beginning was to work on the N-type side with a segmentation. So we have two compositions. One of the compositions is here rather small concentration of antimony. In this case, I think you can use you apply at lower temperatures, and then the higher concentration of antimony is used at higher temperatures. And this gives you some boost in terms of the efficiency. When we do now this combination, this gives you an overview of the thermoelectric properties. Seebeck coefficient is over the whole regime rather high, I would say. Electric conductivity is also rather good. But the important factor is the T number you can see here. When we combine for the N-type materials the segmentation, we keep it on a very high level by the segmentation over the whole temperature regime. And then, for example, the comparison with the P-type material, also over the whole temperature regime, we are, I think, close to a ZT of 1. I think the most recently optimized N-type material even reaches a ZT of 1.4 or so. So it's, I think it has a very promising, results. These were the earliest data. We had here efficiency of about 7% when we did this combination segmentation of the N-type material, P-type as a whole. And we applied here a temperature gradient of 250 Kelvin. And I think this is already roughly now 5 years ago. What is very important always when we design such a module, that we do finite element simulation. So we simulate the whole device, and we also get a very good fit between our actual fabricated device and also the simulations. And you can also play around with the geometrical parameters. In this case, it was not so much necessary to play around with, for example, the cross-section, but there was the idea to maybe optimize it. Here we have to optimize, for example, the height and the segmented, and you can see you can optimize it by the segmentation, this performance. Very important for all the thermoelectric devices, and this also comes into play in these simulations, are in principle the contact resistances. I mean, you can have an excellent material, but if your contact resistance is high, then you ruin every device. On the other hand, you can also have a decent thermoelectric material. If you have excellent contacts, you still get a good device. This is, I think, quite often overlooked when people talk about ZT, that contact resistance is quite, for devices, quite often more important to take a look on it. We also, I think, with the earlier stage, we also figured out that we in principle had a rather small, I think, filling factor, so about 16%, for example. So there are some radiative heat losses. And when we improve, for example, the filling factor, going from 16% to up to 64%, so 4 times higher filling factor, we can significantly improve the device. This was done in this study that we, I think, varied the filling factor, also played a bit around, for example, here with a different configuration, instead of a 2 times 2 configuration with a 4 times 4 configuration. And when we do this, for example, you can see here, when we come to the highest filling factor, 64%, we also have the highest efficiency. So there's a more than 1% gain, so about 8.2% efficiency when we apply a temperature gradient of 260 Kelvin, for example. And if you compare it now with I think, many other materials, also magnesium-based materials, but also bismuth telluride-based materials, we have here the steepest increase of the efficiency. And you can see also quite, I think, nicely this relationship. So if you can, I think, apply here higher temperature gradient, you obtain a higher efficiency. So if you draw up the line, if you could apply, for example, on the magnesium silver antimony at 400 centigrade temperature gradient, you would definitely reach more than 10%. But since we cannot, I think, apply more than 300 centigrade at the moment, just I think with a P-type material, we cannot reach more than 10%. Another strategy is also to improve it. You can also play a bit about the doping and the crystal structure. And this is, I think, very different. The magnesium material behaves very differently compared to the bismuth telluride. Bismuth telluride, you can make very tiny grains and you have a very low thermal conductivity. This is, I think, works quite nicely. Here you have to apply a very different strategy. Here you like to have very large grains because the mobility of the charge carrier is strongly affected by the grain size. So when you come down to, let's say, grains in the range of 100 micrometer, you have here, let's say, mobilities of the charge carrier which are very close to single crystals. And this can be, for example, optimized by changing the compactation conditions. So we use here spark plasma sintering, different temperatures, for example, we applied here. And you can see here when we apply now 100 degrees more, we have larger grains, and then the performance of the power factor is much higher. And you see also here in this formula, 20% excess of magnesium is used here when we apply now the higher temperature. So we have some loss of magnesium, but there are also some ways in future we might have some ways even to work with smaller excess ratios of the magnesium in the production. Playing around with the dopant is also another way to optimize the material, making it even better. Here we took, for example, instead of tellurium yttrium, and this, I think, lead to a higher mobility of the charge carrier, and also, I think, enhanced here the average performance of the T to a factor of 1.1 in this temperature regime up to, let's say, 573 Kelvin. This is another way to boost it further. And this is, I think, now, some optimization. After doing all these optimization steps, you can see here we have an efficiency of 8.5%, for example, on these modules. When we have now the temperature gradient of 260 Kelvin applied. And even if we have moderate temperature gradients, 75 degrees, so just heating the hot side up roughly about 100 centigrade, we have 3% efficiency already. And this is usually, I think, 3% efficiency what you obtain, I think, with most commercial bismuth telluride-based modules when you apply temp at 200 centigrade or 150 centigrade, I think, temperature gradient. Okay, what you also have here are some data points from other modules with higher temperature material like scutrodies, half-Heuslers, for example. You can see efficiency is not higher because they're, on the other hand, performing very weak on the low temperature side, at low temperature. So you can only harvest here from the higher temperature, really the heat, but not from the lower. But if you would combine magnesium antimonide with, for example, a scutrodiide-based module or, for example, half-Heusler, most likely you can reach, I think, efficiencies in the range of 15 to 20%. The other, since I think cooling is the most important market for thermoelectrics up to now, we have tested also the cooling performance. Here delta T was reached of 72 Kelvin. And this module is not optimized for cooling. So we would most likely change a bit the composition of the material. We would also change the geometric parameters for cooling. But this is, I think, some of the targets we want to look in the future to optimize these modules for cooling. Then comes the important factor, magnesium. There are some instabilities and so on. How can we deal with it in terms of cycling test? And we did some rather harsh treatment of these modules. So we treated them, I think, a bit more harsher than bismuth telluride modules. So we heat up these modules to on one side of more than 200 centigrade. Then we let cool it down. The heat up is about roughly 1 minute. The cool down is about 9 minutes. So one cycle is typically 10 minutes. When we repeat this cycle for several thousand times, then we can see the degradation, for example, of these modules by monitoring the internal resistance. First test was done under inert atmosphere in a glove box. They're rather stable. You can see here the degradation of the bismuth telluride-based modules, and they're degrading much, much faster. These are now some tests when we do some cycling of the modules. What is changing? There are some degradation effects, but I think most of the degradation happens at the interface to the soldering. So the weakest point at the moment in our modules are the soldering. But this can be also solved in the future. Talking about, okay, before I will go now, how we, I think, principle fix directly the stabilization. I will shortly talk about also the upscaling. You can upscale the material synthesis for the N-type material rather easily. Kilogram scale should be easily doable. P-type material is a bit more challenging to upscale it, but this also works. The module we are currently fabricating are, for example, these 8x8 configurations. So it's a footprint of 25 times 25 millimeters, for example. The final module, this was a stage when we simulated the whole module, and this we are now fabricating in a larger scale. One of the challenges we figured out when we fabricated, I think now this material in larger scale, also making modules out of it, was the dicing of this material. It takes, first of all, a lot of effort. There are also from Vicente Pacheco some, I think, cost analysis that the dicing process itself consumes a lot of money in terms of the fabrication of the whole module. It's not really the material itself, but the dicing process. What we figured out here was the the N-type material can be diced quite easily within, let's say 1 or 2 hours. Was, I think, rather straightforward, but the P-type material was at the beginning very nasty. So it took days, I think up to a week, I think, to dice just the P-type material. We have now optimized the dicing process. This can be also done now within hours, but at the, let's say, first months, this was, I think, really a bottleneck, just the dicing of the P-type material. This shows a bit the assembly process. So at the moment we have the 8x, we use standard for the assembly, the 8x8 configuration, but there are also some ideas to also go to larger configurations in the future. Okay, coming also, I think, at the end to the stabilization of this whole module. So since we have magnesium antimonides, the risk that there are in principle when they operate in air that you will destroy them is rather straightforward. So what we used is the atomic layer deposition process. And the beauty of this process is that you can use the whole assembled module and coat the whole structure of this module with the film, for example, of hafnium oxide or aluminum oxide. It turned out that aluminum oxide is less ideal, but I will shortly talk about it. But also the most ideal is now silicon oxide and hafnium oxide. These two materials we now use for the coating of these modules. And we coat typically about 200 nanometers of oxide materials. This gives you an impression how, for example, the assembled module, I think, looks like when we are not doing any cycling. This is, I think, for example, a simple module with a 2x2 configuration. After you do, for example, cycling in air, you have here some degradation effects on the hot side, like expected. If you now coat the whole module with hafnium oxide, 200 nanometers hafnium oxide, after the cycling process, there's no strong, I think, degradation effect observable. And also if you do the cycling for a very long time, for example, here this is a module in air, after, let's say, few thousand cycles, you cannot use it anymore. If you, for example, put aluminum oxide on it, it works a bit better for a longer time, but there's the aspect that aluminum oxide forms with magnesium oxide, a rather easily water-soluble oxide, and this also not really protects our module. And therefore, you should use a more robust oxide, like silicon oxide and hafnium oxide. And if you do this, you can see here, if we now cycle this whole module for half a year, it's rather stable. And what we have figured out, I think the weakest point is here the soldering. So if we unsolder the module, resolder it again, we come back to the same performance like we had from the beginning. So the weakest point where we have to do some optimization is the soldering material to find a better way to principally thermostabilize this module. For all the cooling applications, this temperature regime, I think you're usually heating up maximum 100 degrees or so, you don't have to do it. This shows a bit also, I think, all these testing with soldering, unsoldering, for example, operating, let's say, with different coatings here. You can see this material is rather stable. Weakest point in all the study we figured out is in principle the soldering. If you redo the resoldering, you get it back, I think, to the same performance you had at the beginning when you have, for example, the hafnium oxide coating. This gives a very good, let's say, performance. And one of the questions I always get from the thermoelectric community, why are you using hafnium oxide? Main, I think, the answer is here. Hafnium oxide is in the semiconductor community a very important material. This is a process we can nicely, I think, use. But we also have now the process for silicon oxide available, or we might use in future also material like zirconium oxide, for example. Okay, let me summarize my presentation. So we were able to fabricate, I think, from a very sustainable material, P and N-type material, from the P and N-type material, here the thermoelectric modules. Efficiency are about 8.5%. Internally, we might also already have, I think, about 9% now efficiency in this temperature regime. Cooling performance is also very competitive with Lisbon Telluride. Stability is also very slightly changing, about 10% when we do really the cycling for half a year. And there's a lot of opportunity to do this surface modifications, I think, of these modules to stabilize the whole module. A lot of thanks to a number of funding agencies from, I think, MRNet, for example, European Union. We have also we have one ERC, I think, starting grant in this direction. And at the end, I also want to use the opportunity that we have now. We are just starting a doctoral network on thermoelectric cooling with magnesium-based materials. There are at the moment, until the end of April, 15 open PhD positions available. If you, let's say, want to communicate, I think where to find these openings. This is the website where we have for this Marie Curie Doctor Network, the website. And there we can find also these 15 openings. And also here the different partners distributed here from Portugal, Spain, Cyprus, France, and also UK. So we will continue, I think, this type of research in the future. Thank you for your attention.
Thank you very much, Cornelius. Other questions from the audience? No? It was very clear. Bruno, there are no questions? Okay. Yes, just a second. We are getting our next presentation. So thank you very much, Cornelius.
Thank you.